We saw in the last lesson that complex numbers can be added and subtracted. It may be no surprise that they can be multiplied and divided too. We'll look at multiplication in this lesson and save division for the next lesson. Let's start by looking at what happens when we multiply two complex numbers. Let's say we have 4i times 7i. Notice that this time around, that there are no real numbers in each of these complex numbers. Just because a complex number is being represented by b times I doesn't mean it's any less a complex number. Remember, 0 is a real number also. Thus, a plus bi can still be a complex number if a equals 0. It still fits. Looking at 4i times 7i, we can immediately see this as 28i squared. But what is I squared? Remember, it was part of our definition in our first lesson. Recall that I equals the square root of -1. If we square both sides, we get I squared equals -1. Thus we have 28i squared equals 28 times -1, which equals -28. Notice that when we multiply I to itself, we don't get an imaginary unit, but a real number. We'll look at it in another lesson, but I to the n power is cyclic. When I is recorded and n is increasing by 1 incrementally. What happens when the real part isn't 0? Let's look at 3 plus 2i times 1 plus 4i. Does this look familiar? It looks like a binomial product, and we learned how to simplify those when we learned about polynomials. Let's go ahead and apply the FOIL rule here. 3 plus 12i plus 2i plus 8i squared equals 3 plus 14i plus 8 times -1, which equals -5 plus 14. We have obtained one complex number. Notice that even though we used FOIL, we didn't get what we normally would have with real numbers and variables. Normally, using FOIL on two binomials would produce a quadratic equation. But here, we simply produced a single complex number. Thus, we can safely say that multiplication of two complex numbers, when a does not equal 0, produces a single complex number. Otherwise, when a equals 0, it will produce a real number. Number 1, 3i plus 5i. These complex numbers have no real parts, so we know we're going to end up with a real number. We can easily multiply the coefficients together. 15i squared. Remember that I squared equals -1. So we end up with 15 times -1, which equals -15. Number 2, -5i times 2i. Just like last time, our complex numbers have no real parts, but one of our coefficients are negative. This changes nothing and we can continue normally. -10i squared. Since our coefficient is negative, this time our real number will be positive. -10 times -1 equals 10. Number 3, the square root of -50 times the square root of -72. Here we have two square roots with negative radicands. Let's factor them into something that we can work with easily. The square root of 25 times 2 times -1 times the square root of 36 times 2 times -1. Since each radicand has only one term, we can simply take the root of the two principal squares, and also simplifying the -1 part. 5i square root of 2 times 6i square root of 2. Next, we can combine like terms. 30i squared square root of 4. Remember, a product of radicals is equal to the radical of the products. Finally, we can simplify our expression. 30 times -1 times 2, which equals -60. Number 4. 4 minus 3i times 5 plus 3i. Here we have a product of two complex numbers proper. Let's use the FOIL method to expand our expression. 20 plus 12i minus 15i minus 9i squared. Now we can simplify. 20 minus 3i minus 9 times -1, which equals 29 minus 3i. We've seen that we can use the distribution property of multiplication to expand and simplify a product of complex numbers. It seemed at first that FOIL was only to be used to multiply polynomials, or more specifically, binomials. But now you're starting to see that techniques and methods aren't proprietary. There are many methods that can be used interchangeably with different types of math. And you're going to see another example in the next lesson. You're going to see that you cannot divide complex numbers without using conjugates.